Hi, chemistry students. This is your lesson, your introductory lesson on covalent molecules. And specifically, we're going to talk about how you use Lewis dot diagrams to draw the structures, sometimes called the structural formulas, of covalently bonded molecules. So just as a review, you should remember that covalent compounds are composed of all non-metal elements. For example, a good example of a covalent compound would be sugar, C12H22O11. It's a very large molecular compound that is consisting of only carbon, oxygen, and hydrogen, which are all nonmetals. Covalent compounds can exist as solids, liquids, or gases. A good example of a covalent compound that exists at room temperature as a solid would be sugar, just as we showed you. It's just carbon, hydrogen, and oxygen. A good example of a covalent compound that is a liquid at room temperature would be water, H2O, again, all nonmetal elements. And then a good example of a gas that is a covalent compound is carbon dioxide, CO2, which again is all nonmetals but exists as a gas at room temperature. Most covalent compounds are molecular. That means their smallest unit is a molecule, and they generally have low melting points. If they're solids, it's not too hard to melt them. The smallest unit of a molecular covalent compound is a molecule. Now, there is one exception to this, one kind of covalent compound that is not a molecule, but the vast majority of covalent compounds that you run into, or covalently bonded substances that you run into, their smallest form is a molecule. The one exception is that there are a few covalent substances that are network solids. Network solids are continuous arrays, sort of like what you see in an ionic compound. Just they are bonded using covalent bonds. Good examples of those would be diamonds, which is just pure carbon. It's an element, actually, an element that is covalently bonded, or sand, whose pure form is silicon dioxide. And instead of having molecules, the covalent bonds just kind of go on forever and ever. Now, these covalent substances that are network solids have very, very high melting points, similar to the very, very high melting points in the strongly bonded ionic compounds. But let's go back and we're going to look at mostly this unit, molecular covalent compounds. Now, molecular covalent compounds are non-electrolytes. In other words, when they dissolve in water, they will not conduct electricity because the atoms that make up the molecules do not break up into charged particles. This is in contrast to ionic substances, ionic compounds, that do break apart into the constituent ions and therefore provide the moving charged particles needed to conduct an electric current. So we're going to talk about Lewis dot diagrams and how we can use them to draw the structures, or sometimes called the structural formulas, of covalent compounds. So let's just get some ground rules here. For covalent compounds to form, nonmetals share electrons so that each atom feels it has a full outer energy level. In this way, they obey the octet rule. When they share, we say they are bonded. So unlike ionic, where we have a transfer of valence electrons, in nonmetals and covalent bonds, we share the electrons. Now, you can build and draw some simple covalent compounds. Nonmetals can share one pair, or a pair is 2 electrons, or 2 pair, and 2 pairs 4 electrons, or 3 pair, which is 6 electrons, in order to feel that they have 8 electrons, or the octet rule. Now, the only major exception, we'll talk about a couple, is hydrogen, that is satisfied with just 2 electrons because that makes it look like the element, the noble gas helium. Now, one good rule of thumb as you're drawing these structures is to remember that elements only bond with their unpaired electrons in the Lewis dot diagrams. So let me give you a couple of pictures. Please just look at these right now, and then we'll go into the rules. So this is the Lewis dot diagram showing the formation of some single bonded molecules. So the first one you can see here is the bond between 2 chlorine atoms. And again, each chlorine atom needs one more valence electron to fulfill its outer electron shell to look like a noble gas. Now, neither one is going to just give one away. They are both so close. However, if they pull the unpaired electrons between them, share it between them, as long as they stay together, each chlorine feels like it has a full set of 8, and as long as those 2 electrons stay between them, they are very stable, and you get this very stable Cl2 molecule. Now, in contrast, just to remind you about hydrogen, again, chlorine needs just one more to feel like a noble gas, and indeed hydrogen, even though it only has one, needs just one more to feel like helium. So again, if they pull their electrons and put them in between themselves, and don't break up, it's sort of like they're holding hands. As long as they are holding hands here, bonded right here, everybody feels like a noble gas. And this would be a picture of the molecule HCl, where both have the complete octet. Okay, so a bond can either be represented in these structures as 2 dots, or if they're bonded, we can use a line. So with a line, we get these sort of structural formulas, okay? So one line equals 2 electrons. So here is, again, the formation of the covalent compound with covalent bonding, CH4, methane. And there are 2 ways to look at this. This is unbonded. Everybody's unhappy. Carbon has its 4 valence electrons as represented by its Lewis dot diagram, and there's hydrogens, 4 hydrogens with its 1. Now, if they kind of come together and they put their 2 electrons between them, and notice how they kind of go around as if they were noble gases. It's not a straight line here. It's 2 electrons in between them, and if they do that, it feels like the carbon has 8 and each hydrogen feels like it has 2. Now, a shorter way to do that is if you have just 2 electrons in between, you can draw lines connecting them, and that line represents 2 valence electrons. Okay, let me show you another one. Again, we're just looking at these. I wouldn't necessarily be writing them down. We'll do some examples. But here is 2 oxygens. Oxygen, as you know, is diatomic. And how do they bond to make an O2 molecule? So in the case of oxygen, they actually share 2 pairs. So here are the unbonded oxygen atoms, very unhappy, only having 6 valence electrons. There are 2 unpaired electrons on each one. Now, what they do is they take these unpaired and they kind of push them in between. They share them. And you can see in between, if they put these 2 and these 2 in between, and they both still have their 2 pairs that are, already here, then you have essentially what looks like 8. So this oxygen has the non-bonding pair on the top, the non-bonding pair on the side, and it is contributed to these 4 that are here in the middle called the bonding pairs. And so if you sort of think about what's like adjacent to this oxygen, you have 8, and you also have 8 over here. And so you have a complete octet, fulfills the octet rule. Now, since we have 4 in the middle, and each one represents a bond, we put 2 lines to represent 4 electrons. So with the lines, we call them structural formulas. With the dots, we sometimes call them still dot diagrams. And finally, nitrogen can actually, and will actually share 6 electrons. Notice it has 5, but there's one that's paired up, but it will, if they take the unpaired electrons and move them for each one of these nitrogens to the middle, then this nitrogen feels like it has 8 as long as we're together, and this nitrogen feels like it has 8, and these pairs on the outside are called non-bonding pairs, but they're sharing 6. Sharing 6 would indicate 3 lines. Okay, so that's kind of the general idea. But I'm going to show you a method by which you can vary by just going 1, 2, 3, 4. You can write and be sure that you're doing these structural formulas correctly. So you may want to copy this down. This is something called the honk rule, or maybe the ha-honk rule. You should write down this rule. in Lewis dot diagrams, elements usually only share unpaired electrons. That tells you the number of bonds that they will make, the number of other atoms that they will connect to. So in the case, the honk rule is, a very easy way to do this is, or the honk rule, is hydrogen and the halogens, which have one valence electron and 7, and are just missing one. They are just one away, will only bond with one other element. So they will only make one bond. Oxygen has 6 valence electrons. It has 2 electrons that are not bonded, that are unpaired, and so it will make 2 bonds. Notice there is a hole here and there's a hole here, so it will make 2 bonds to fill those holes. Nitrogen has 5 valence electrons, so in its electron dot structure, it actually has 3 empty seats, 3 holes, 1, 2, 3. So it will make a bond so that it can fill those 3 empty seats. So it makes 3 bonds. And carbon, which has 4 empty seats, will make 4 bonds. Okay, so you're going to use this to figure out how to put these elements together, these non-metal elements together in molecules that make sense. All right, so again, the honk rule. Hydrogen and the halogens form 1 covalent bond. Oxygen and sulfur form 2 covalent bonds. Now that could be a double bond as the 2 or 2 single bonds. Nitrogen and phosphorus form 3 covalent bonds. Now that could be 1 triple bond or 3 single bonds or 1 double bond and a single bond. It just has to have 3 lines coming from it. And carbon and silicon, and again, the reason for this is that nitrogen and phosphorus, oxygen and sulfur is again because they have the same number of valence electrons. So carbon and silicon can form 2 double bonds, 4 single bonds, a triple and a single, or a double and a single. Okay, we're going to watch a very short video on this that comes from Science Geek.
When drawing Lewis structures, we rely in large part on the octet rule, but I also find it useful to teach students the honk rule. Now understand these are rules, they're not immutable laws of science, and so there are going to be exceptions. Nonetheless, most of the time, these rules apply, and they help us in deciding how many bonds will be around any given atom in a covalently bonded compound. So it goes like this. Hydrogen and the halogens will form 1 covalent bond in covalent molecules. Oxygen and the oxygen family, meaning the nonmetals in the oxygen family, will tend to form 2 bonds. Nitrogen and the members of the nitrogen family, in particular phosphorus, will tend to form 3 bonds. Carbon and the carbon family, in this case limited to silicon, the only other nonmetal, will tend to form 4 bonds. If you look at the periodic table above, we have hydrogen and we have the other nonmetals, excluding the noble gases, which tend not to form covalent bonds. So let's look at how this is useful in drawing Lewis structures. So hydrogen in a chemical compound will tend to have a single covalent bond, because hydrogen will only end up with 2 electrons around it. That bond, which is essentially 2 shared electrons, will suffice. The halogens, on the other hand, we'll take chlorine as an example. The honk rule says chlorine will form a single covalent bond. To get its octet, it's going to have 3 pairs of electrons that are not shared covalently. And that will be true for the other halogens as well, fluorine, bromine, iodine. The members of the oxygen family tend to form 2 bonds. Now there's 2 ways that that can happen. Oxygen could have 2 single bonds, and that would necessitate 2 pairs of unshared electrons, 2 unshared electron pairs. Another possibility is that oxygen could form a double bond with one other atom. And again, we're going to get 2 unshared pairs of electrons. Nitrogen and the nitrogen family tending to form 3 bonds. can do that 3 different ways. Nitrogen could form 3 single bonds, which would require 1 unshared pair. Nitrogen can form a double bond and a single bond for 3 bonds total and an unshared pair. Or nitrogen can form, as it does in hydrogen cyanide, a triple bond and 1 unshared pair. Notice there's some generalities here. The halogens are always going to have 3 unshared pairs around it. Oxygen, 2 unshared pairs. Nitrogen, 1 unshared pair, which should lead to the conclusion that carbon will not have any unshared pairs in most covalent compounds. So carbon's possibilities are going to look like this. Carbon can form 4 bonds. It could be 4 single bonds. That gives it an octet, no need for unshared electron pairs. Carbon could form a double bond and 2 single bonds for its 4 bonds. Carbon could form 2 double bonds, or carbon can form a triple bond and a single bond. There's no such thing as a quadruple bond. And in all of those instances, carbon gets its entire octet from the bonding electrons and has no need for unshared electron pairs. That's the usefulness, again, of the Honk rule.
Okay, so at this point, I am going to move on to a different lesson. In the next lesson, we will talk about examples of doing using the Honk rule to actually draw these structural formulas. But we'll take a break here at this point in the lesson.